Hey everybody, got a couple of more reactions, a couple more videos, and we're going to write the equations for those reactions. And we'll just kind of talk ourselves through this here a little bit. For the first reaction, we had a couple of solutions here. We had copper 2 chloride solution, which is that nice pretty blue solution, and sodium phosphate, which is clear and colorless. So let's start with our reactants here, of course, and write the formulas for those and get state symbols. So copper 2 chloride, of course, the 2, the Roman numeral 2 means copper with a +2 charge. Chloride is a -1, and so our formula for copper 2 chloride is going to be CuCl2. And as I said, that is a solution, so it's an AQ. Our other reactant, of course, here is sodium phosphate. Sodium's in the first column, so it's a +1. Phosphate is PO4, and phosphate all together here. In fact, let's just take a look at phosphate on our polyatomic ion list. It is down here in the -3s. So, there we go. So phosphate is a -3, sodium is in the first column, so it's a +1, so our formula here should be Na3PO4. So those are our two reactants. Oops, I forgot the AQ here on the sodium phosphate. All right, so I don't think I told you what type of reaction this was, but as I was talking about the other day, if it's going to fit into one of our 5 categories, then they all have a certain look to them. And so right off the bat, you can kind of tell what this is going to have to be. We've got 2 compounds, 2 ionic compounds in solution, and so what that means is that they are going to trade partners. In other words, the copper is going to go with the phosphate, and the sodium is going to go with the chlorine, the chloride. And of course, this is going to be a double replacement. The copper is replacing the sodium, but at the same time, the sodium is replacing the copper in this compound over here. So what that means for us, of course, is we've got 2 new partnerships here. The sodium, as I said, is now with the chlorine. Sodium +1, chloride, I should say, ion, -1. And then the copper 2 is with the phosphate. And this one, of course, the copper 2, that means a +2 charge. Right? Just draw it up here, +2. And the phosphate, as we said, is a -3. Well, we've got that 2-3 thing going that we find a lot of times, right? Which means we need 3 coppers and 2 phosphates, but because it's a polyatomic ion, it has to go in parentheses like that. Okay, now for the state symbols. So the way these double replacement reactions work, when you get your 2 new compounds over here on the product side, one of these guys is going to form a precipitate. And in fact, I've got a picture of that, right? I attached that picture. This blue kind of chunky looking stuff is the precipitate that sort of, you can see it's sort of settled to the bottom here after it's set in there for a few minutes. So that's the precipitate. Our task is to figure out, okay, which one of these guys is the precipitate and which one of them is dissolved. So to do that, we follow what are called solubility rules. So the solubility rules, I have them conveniently printed on the bottom of our periodic table, the back side of the periodic table, right, with all the polyatomic ions. If you look down here at the bottom, we've got solubility rules. And they basically come in 2 categories here. On the left-hand side, we've got a list of, if a compound contains these ions, then it is probably soluble. And then on the right-hand side, 6 through 10, if a compound contains these ions, then it's probably insoluble, but you can see there are lots of exceptions. So let's just kind of work through this here and see what ones apply. Rule number 1 here says alkali metal ions or ammonium ions. So in other words, if our substance contains an alkali metal, well, where are the alkali metals? They're in the first column. Well, alkali metal, that's sodium right here. Sodium is an alkali metal. And again, according to our solubility rules, that says that compounds that contain an alkali metal are usually soluble. Okay? Um, the yeah, so that probably means that guy is going to be soluble. Okay. Let's see what else we've got going on here. We've got a phosphate in the copper phosphate over here. Okay. Well, the copper 2 phosphate. If I look over here on rule number 8 says compounds that contain the phosphate ion are usually not soluble. They are insoluble. And rule 1 exceptions. Rule 1 exceptions means, well, if it has one of those alkali metals or the ammonium ion, that it's probably soluble. So let's look at what we've got here on our equation over here. On the product side, we've got a phosphate ion with copper. Copper is not one of those alkali metals. Over here on the reactant side, the phosphate was with the sodium, so that is soluble. But on this side, it is not. So in other words, that means this guy is our precipitate, and its state symbol is going to be S. And over here, the sodium chloride, that is going to be an AQ. That is going to be dissolved. And you could probably figure that out on your own if you remember, of course, that sodium chloride is just regular old table salt. Of course, we know that that dissolves in water. But the point is, we can use those solubility rules to figure out which one of our new products in these double replacement reactions, which one is the precipitate and which one is still dissolved in water. All right, so the last thing we need to do is that we need to sort of clean this up a little bit by balancing the equation, right? I've kind of made a mess of it here by writing all over it. But we've got 2 phosphate ions on the product side, so we need 2 phosphate ions over here, so I need a 2 in front of the sodium phosphate on the reactant side. Now, you might notice that gives me 6 sodiums. So if I'm going to get 6 sodiums on the product side, I need a 6 out in front. Remember, the only numbers I can change, once I have those formulas correct, once I have those charges balanced and the correct formulas for all my reactants and products, the only thing I can change is the coefficient out in front. So now I've got 6 sodiums, but I've also got 6 chlorines now on the product side. So if I go back here over onto the reactant side, that means I'm going to need a 3 in front of copper 2 chloride to give me 6 chlorines. Well, that also gives me 3 coppers, but if I look back over here on the product side, I already have 3 coppers. So now I believe everything is balanced, right? 3 coppers on both sides, 6 chlorines on both sides, 6 sodiums on both sides, and 2 phosphates on both sides. So this one's all balanced up. It's kind of a mess there, sorry about that, but it is all balanced up. And we've got the state symbols, and we figured out what our precipitate is and all that fun stuff. All right, for the other reaction, we've got ammonium carbonate. So ammonium carbonate is one of those that includes 2 polyatomic ions. Remember, ammonium is our one and only polyatomic ion that is a positive charge. It's not the only one that exists, but it's the only one that's on our list. It has a positive 1 charge. Carbonate, which is CO3, has a negative 2 charge. And so if I'm going to balance out the positive 1 with the negative 2, I got to put this guy in parentheses and put that 2 down there. So now remember what that 2 means. It means 2 ammoniums, which means 2 nitrogens and 8 hydrogens now, right? Remember that 2 multiplies by everything in those parentheses. Let me go ahead and clean that up a bit so we can get that out of our way. All right, so here's the little bit of tricky part about this one. I had a lot of people that wanted to do this as not a combustion, but wanted to, put it that it was reacting with oxygen, probably because we were heating it up and it kind of disappeared or whatever. But when we say, when something, gets heated up and it reacts with oxygen, that usually means that it's burning. Well, this guy didn't really burn. If you remember from the video, it didn't burn. It just kind of disappeared, right? It was in the bottom of the test tube, a white chunky solid in the bottom of the test tube. And as I heat it up, it just kind of gets smaller and smaller and smaller and eventually just kind of goes away. Other thing you might remember is, so anyway, my point is that it's not reacting with oxygen. In fact, it is the only reactant. Ammonium carbonate is the only reactant. This, of course, means that it is a decomposition reaction. Decomposition reaction, you can recognize that by the fact that there is only one reactant. It is one single compound that decomposes or breaks apart into multiple products. So here's the tricky part. What are those three products? Well, they're all colorless gases. You can't see them. It sort of looks like I said that it just sort of disappears. Well, it doesn't really disappear, but it leaves as a gas, or actually a few gases. So if you recall, I tested that gas a few different ways. I put some cobalt chloride paper down inside there. And what cobalt chloride paper does is, if it comes in contact with water, it turns from blue to pink. It's a substance, an ionic compound that when it's anhydrous, it's blue, and when it's hydrated, it's pink. And so if you recall from the video, it did turn a little bit pink. Not a real strong indication there, but it did turn a little bit pink, or at least got much lighter in color. And so that tells us that, yes, indeed, there is some water vapor. Remember, that is in the gas state, right? Because we didn't see any liquid drops or anything like that. We detected the water vapor with the cobalt chloride paper. The other thing that I mentioned in the video is it had a very strong odor of ammonia. Ammonia is a substance, once you smell it, if you know what it smells like, it's very recognizable. It has a real nasty, if you've ever used smelling salts, or it's in a lot of cleansers like glass cleaner and stuff like that, it has a real sort of pungent smell to it. Now, here's where I kind of left you hanging a little bit. Ammonia sounds a lot like ammonium. Well, ammonium is the NH4, right? That's the polyatomic ion, NH4 with a +1 charge. Well, this is ammonia with the formula NH3. And I sort of tested that a couple of ways. First of all, I could smell it. It's a very strong smell that's given off. The second way is that ammonia is a base. And when I tested with some litmus paper, it indeed turned the red litmus paper blue. And when you test with litmus paper, litmus is a simple acid-base indicator, and B is for blue and B is for base. So that red litmus paper turned blue, or blue litmus paper will stay blue. That indicates a base. Okay, and then the third thing I tested for, I took a wood splint and kind of stuck it down the mouth of the test tube. Now, we've seen this a couple of times before. I lit the gas in the balloon with a lit wood splint. I put the wood splint into the bubbles from that big foamy hydrogen peroxide reaction. In the first case, the gas was burning. That was hydrogen gas in that balloon that was burning when I hit it with the wood splint. Or the burp test from the other day. In the case of the bubbles in the foam from the hydrogen peroxide decomposition, it didn't burn the gas, but it sort of made the wood splint flare up a little bit. That indicated oxygen. The fancy way of saying it is that gas, that oxygen, supports combustion. Well, if you remember from this video, what happened when I stuck the wood splint into the mouth of the test tube is the wood splint went out. It extinguished the flame. And so another way of sciencey way of saying that is it does not support combustion. And that is a real simple test for carbon dioxide. Okay, and again, that's a gas. So those are our three products. There's actually a better test for carbon dioxide that I'll put in a different video for you. But anyway, that wood splint, putting out the wood splint is a good simple test for carbon dioxide. All right, so these are our three products. Again, decomposition we notice because we've got one reactant that breaks apart into multiple products. Now we've got our correct formulas and we've got our state symbols. We just need to balance it up a little bit here. All right, so first off, this one it's actually deceptively easy, but it can be a little bit tricky because you got, obviously you've got everything locked up into one compound here on the reactant side, and then you got to find, it ends up in three different places over here. So it can be a little bit trickier, or seem trickier than it really is. If you latch on to the idea that this 2 right here, subscript, that gives us 2 nitrogens, That's the key right there, because the only way we can get 2 nitrogens on the product side is to put a 2 in front of ammonia, the NH3. Once we do that, I think you'll find everything else just sort of falls into place. So let's check it out. We've got our 2 nitrogens here, just like we needed. Remember this 2 on the reactant side, that 2 subscript gives us 8 hydrogens. Well, we've got 6 hydrogens here, right, on the ammonia, but we've got 2 more over here. So that gives us a total of 8 hydrogens. We've got 1 carbon in our carbonate on the reactant side. We've got 1 carbon in carbon dioxide on the product side. We've got 3 oxygens on the reactant side. We've got 2 oxygens in the carbon dioxide, but another oxygen here in the water. And so this guy is all balanced up. Everything balances out with just adding that 2 in front of the ammonia. Okay, well, I have talked here long enough. So I hope this helps. And I'm going to send you out a couple more of these. And we'll just kind of keep practicing this a little bit longer. And until we feel a little bit more comfortable with it. So hang in there. Please send me questions by email if you have any. Some of you have been asking some good questions, and I'll try to get back to you pretty quickly. And you've been working your way through those problems, and I'm very proud of you guys. Hey, take care of yourselves, stay safe, and please let me know if I can help you in any way, not just with schoolwork, but with anything. All right? Take care.